Okay, so I've been asked to introduce Mark at short notice. And this means, of course, Mark, that I can say anything.
You normally have a script then.
Well, but it's even worse than that. Of course, anyone who is part of the speech community knows who Mark is and what he does. For the benefit of those of you who, maybe several of you in the audience who don't know, Mark is probably best known for his work on linear transforms in speech, things like speaker adaptation, that kind of stuff. That's what people know him for. But you find out if you mention your own work to him that almost anything that people try, Mark has tried 10 years before with a much more rigorous derivation. So he can be annoying in that way, but there's not much you can do. Okay, so I don't really have a great deal more to say. So I'm going to hand it over to Mark.
Well, thank you for that charming introduction, Dan. It really set the scene and made me feel good about myself. And I have done it all before. So what I'm going to talk about today are sequence kernels for speaker and speech recognition. Part of the motivation for talking about this sort of area, in contrast to, say, our the various bits of large vocabulary stuff we do in Cambridge, is partly linked to the workshop and the sort of work that Dan's doing at the moment, where they're trying to take some of the ideas from verification and speaker recognition area and applying it to speech. So I thought I'd go along with that sort of general theme. So this is work with some of my students and RAs in particular, Martin Layton, Chris Longworth and Federico Flago. So a quick overview of what I'm going to talk about. I'll start off by motivating all the work from support vector machines and kernels. Discuss very briefly what static kernels are and what the text-independent speaker verification problem is. This will lead on, hopefully quite naturally, to the use of sequence, sometimes referred to as dynamic kernels. And this will allow us to apply support vector machines to data such as we see in text and speech. And I'll split those kernels up into three basic areas. Discrete observation kernels, string kernels for example, distributional kernels, and generative kernels and score spaces associated with them, which we can apply to continuous data. I'll look at how we could use them for speech recognition rather than the text-independent speaker verification. And I'll finally finish on applying the techniques and ideas to a noise-robust speech recognition task. Hopefully everyone's familiar with support vector machines. Very, very basic. They're max and margin binary classifiers, build linear decision boundaries. They aim to try and build the decision boundary which maximizes the distance between the two closest points to that decision boundary. They're nice, kind of related to minimizing generalization error. They've got unique solutions. And really the nice part about them is that because the training and classification can be written in terms of inner products of test and training examples, they can actually be kernelized. And I'll show what that means on the next slide. What we'd like to do, one area that I've been working on for a few years, and other people have as well, is how we can actually use support vector machines and related approaches to speech recognition. So what's the kernel trick? Well, the kernel trick is sort of summarized by this diagram. You can imagine having some data in a two-dimensional input space. What we'll do is we'll do a nonlinear transformation from that input space to some feature space. And what we'll do is we'll build a linear classifier in that, hopefully a higher dimensional feature space. And what we'll do is, because we built a linear decision boundary in the higher dimensional feature space, when we look at the effective decision boundary in the original space, we've got a nice nonlinear decision boundary. There's a series of very standard kernels associated with SVMs. So you've got linear kernels, basically simply take the inner product of training observations or training and test observations. Polynomial kernels, dot product, add 1 raised to a power. And Gaussian or radial basis function kernels, exponentials of Euclidean distances divided by twice the square of the window width. These are all well and good, but they do rely on the fact that each of our observations, the xi's and the xj's, are of the same dimensionality. So we can apply them to fixed length observations for both training and test. We're looking a little bit more detail at the nature of a particular score space or feature space this is associated with polynomial kernels. So the top bits are just really building a real decision boundary based on, this is the iris data from many, many, many years ago, lengths of petals and related bits from a series of irises, split into two classes. On the left, we've got a linear kernel, very, very poor performance. On the right, we have a homogeneous polynomial kernel. That just says there's no +1 in the kernel. So what's the effect if feature space is associated with it? Well, what we're going to do is we're going to say this is our nonlinear transformation of our input features, which are two-dimensional. And what happens is if we map them into this via nonlinear transformation into this three-dimensional feature space, simply the first element squared, square root of 2 times the product of the first and second elements and the second element squared, then when we work out the kernel associated with that feature space, when we take the dot product of them, it's exactly the same as if I'd simply dot producted the two original vectors and just squared it. So the nice thing about most kernel operations is that they can be written simply as operations in the input space, which is exactly the same as taking dot products in the feature space. I'm actually not going to, when we talk about sequence kernels, this is one of the limitations with various bits of the sequence kernel work that I'm going to discuss later, is for a range of them, we actually can't do this nice trick of being able to work out the effective kernel operation by having some nice low-dimensional dot products. But we can still use the general concept of taking some nonlinear transformation of the input space into some feature space and operating in that feature space. So to motivate the concept of sequence kernels a little bit more, we'll consider the kind of one of the original applications of support vector machines in the speech processing area, which is verification. So this is kind of a standard verification framework. We start off with speech on the left. We do some feature extraction stage for it. We then take the features, typically extract at a 10 millisecond frame rate, and we feed them into some general speech model, universal background model. We get a log likelihood score from that. We then feed it into a speaker-specific model. So I should have said speaker verification. Are you actually the person you claim to be? Yes or no, simple binary task, nicely suited for SVMs. So you have the speaker model associated with the person you claim to be, work out the likelihood or log likelihood associated with that, then you have some decision based on a threshold. Typically for text-independent verification, you work with a Gaussian mixture model in order to work out the similarities. And this is actually really nice. We just compare those likelihoods and pick one. So the real issue is how we can take this general verification framework and apply support vector machines to it. And to do that, we're going to need sequence kernels. So they're quite nice. What they do is they say if you've got speech, we've parameterized our speech at 10 millisecond frame rates. Even if I say the same word twice, so 1 and 1, they're actually going to be different durations. So I'll have a different number of frames. So I can't simply take the dot product of all the frames from one utterance of the word 1 and dot product with all the frames of another utterance of the word 1 because they're different lengths. I can't do it. So in order to allow me to do that, we're going to use these sequence kernels. So what they need to do is basically take variable length sequences and map them into a fixed length feature vector. And that feature vector I can then do dot products or any other operations I want to actually allow me to use support vector machines and other kernel operations on them. This sort of task is applicable in a range of areas. So there's lots of biological applications, text processing applications, and the one I'm going to concentrate on, which are speech applications. These sequence kernels can be roughly split into 3 broad areas. The first one's associated with discrete observations. So that's where we can do text processing. And string kernels are the classic standard operation for that. The second one, which is associated with, or can be associated with continuous data, such as speech, is distributional kernels, where we're going to look at the distances between distributions trained on sequences of data. And the final one is generative kernels, which again are appropriate for continuous data, where we'll actually look at extracting either parameters or features of generative models, such as Gaussian mixture models and hidden Markov models, to form our feature vector. So,
back up one slide.
Yep.
So when you say distributional kernels, you're excluding, for example, parametric generative models from it, because I could think of taking the two sequences, fitting a parametric model with the same set of parameters to each of them. And then, so would that be a distributional kernel? Or?
So that would actually be a distributional kernel if you're actually training a parametric form of a probability density function on the data from one sequence.
Right.
You work out probability density function for the data from a second sequence. And I'm just going to look at the distance. Yeah, just happens that one of classic forms actually, which is the GMM mean-Supervector kernel,
Right.
actually belongs to generative kernels as well.
Okay.
So that's roughly the split. One is being a little bit more explicit that it's associated with either the parameters or derivatives of the generative model, whereas the distributional kernel, very general, just the distances between distributions. So the string kernel is kind of a very standard form of kernel that allows us to look at, well, in this case, I'm going to just look at it at a character level, which says if I want to look at the distance between cat and cart, how can I do that in a way that maps, well, one is a sequence of 3 characters, one's a sequence of 4 characters. How can I get them so I map them into a fixed dimensional feature space that allows me to do dot products? Well, the simplest way is to say, let's look at all possible pairs of characters that can occur in the set of words cat, cart, and bar. So we've got CA, CT, CR, etc. What we'll do is where that pairing occurs next to each other, we'll give that a value of 1. Where they occur when they're split, so that there's, for example, a character between them. So we've got the word cat, where we've got the pairing CT in there, but it occurs with A between them. We'll say, well, we'll give that lambda. If there's 2 words between them, we'll give it lambda squared, and carry on like that.
Is this like a standard form?
Yeah.
It seems a little bit strange.
In what sense?
Well, I mean, the concept of having a lambda depending on how far it is, I mean, can you just introduce separate variables for how far? Or?
It's, well, you've effectively done that, but you've fitted it. So it saves time. So you kind of got to pick a value if they're 1 away, 2 away, 3 away, 4 away. What's the easiest way of doing that? You just pick a value lambda and then square it, cube it, raise it to a 4. And yes, it is a completely standard form. So what you can then do is you can take each of the words that we're interested in here, cat, cart, and bar. We map them into the feature vector associated with, well, this space of CA, CT, CR, AR, etc. And we get scores like this. So cat has CA1, CT lambda.
Yeah.
I haven't got AT on there, of course, so I don't have the complete space. And I've got this set of feature vectors associated with cat, cart, and bar. Each of these are now of the same dimension. So it's quite easy. If I want to now look at the distance between cat and cart, I simply take the feature vector associated with cat, the feature vector associated with cart, take the dot product of the 2, and that gives me a score. In this case, 1 plus lambda cubed. Very nice, very simple. You can run this at the character level, the word level, etc. And it's very simple. But that's actually kind of interesting, but a little bit painful if you're going to actually run this and actually map every word into the full set of possible pairs and extensions to the pairs of all the characters. So how can we make this more efficient and more general? Well, there's actually quite a nice generic way of doing this, which are called rational kernels. So these are a way where we can actually represent a whole range of possible kernel operations within a consistent single framework. And this covers bag of word kernels, n-gram counts, gappy n-grams, which is an example of the string kernel. So what you do is you actually use a weighted finite state transducer. And you have an operation like this. I'm not going to go through it, but you get this nice operation that if you write an appropriate transducer for it, and then you want the kernel operating between two sequences of words, for example, then you can simply say that is actually an operation of taking the transducer, composing it with the transducer inverse, and composing it with each of your observations. What you can do to get different forms of kernel now is you simply swap the transducer you're operating on. To give you here a gappy bigram, you just can do it for n-gram counts, etc. This is nice. I can actually simply run this transducer. I don't have to explicitly produce the whole feature space associated with all possible word pairs. I can also operate, if I was to, for example, extract text from an ASR system, I can actually feed lattices into this. And then I can run these transducers on lattices going in, and I can get the distances between observation and text sequences from speech data. And this has been applied in a range of areas. What's interesting is you can actually also do this for the derivative generative kernels that I'm going to describe later.
Mark, then to answer Dan's question, again,
Yeah.
I want to quickly go back to the previous slide. The reason why you have this particular choice that distance 1 will be called lambda, 2 might be called lambda squared, is because it then enables you to compute that kernel using these machines, meaning the two kind of go hand in hand, don't they?
No, I think you could, I'm pretty certain you could set up a transducer to allow you to have arbitrary distances by expanding out this central node. It's this central node aspect that allows me to read in as many in this case, A's and B's.
So if I had arbitrary lambda 1, lambda 2, lambda 3 for distance 1, 2, 3,
it would just sit in here.
You would see a more crazy machine.
Yeah, it would just be a crazier machine. But then you've still got to set, what's a sensible way of setting the lambda as I change the distances between them?
What is the inverse defined as?
You just swap the inputs and outputs
Okay.
of your transducer. Yeah?
What would the positive definiteness of this kernel, or
This one is positive definite.
what does it even mean?
Sorry,
What does it mean for this kernel to be positive definite? For all possible.
it means that it's going to be symmetric and you're going to always get out positive scores for it. For any pairing AB is the same as BA, and all the scores will be positive. So there are kernels which we typically use for text-style applications where we've got discrete observations. So how can we swap this to look at continuous observations which we care about for speech? So we can look at distributional kernels where you can imagine deciding that I'm going to have a form of distribution. So we've got some probability density function here acting on the observation sequence with parameters lambda. So what I can do is I can take the data from one particular sequence, make, in this case, a maximum likelihood estimate of the model parameters associated with the observation sequence OI to give me lambda I. I can do it for another observation sequence OJ to give me lambda J. And now I've got two distributions. And I'm going to say that these distributions are close when a distance between those distributions is small. The natural way to pick a distance between them is to either use something like the Coulpach-Leibler divergence, which is just the expected value of the log of the ratio of the likelihoods, or we could use the Bhattacharya affinity measure. So these are both standard forms and allow us to have a completely different form of kernel operating now, which just requires us to be able to estimate in some fashion distributions on the observation sequences. So let's look at a particular example of this, which is the GMM mean-Supervector kernel. So kind of starting from that concept of distributional kernels, you say we would like it because we're going to use this with support vector machines to be positive definite. So we make the kernel symmetric. We then use the matched pair approximation for KL divergence because we know that when we're dealing with things like Gaussian mixture models, there's no neat closed form solutions for looking at the KL divergence between GMMs. We then further assume that GMMs are only going to differ according to the means, and we'll use the polarization identity. We do all of that And we end up with a kernel that looks like this, which says simply take your distribution, your GMM, for each sequence, work out, using typically the map estimate, what the map estimate of each of the means of your GMM are for observation sequence I, each of the means are for observation sequence J, and then you just work out what this is, sum over all of your means, and you weight it by the prior. So that's quite nice. We're actually sitting there, we can take any arbitrary sequences in, we map them to a fixed length, and we can take dot products. This really comes back to the nice, sorry.
Yeah, sorry, what if the component one, mixture component one in the first model is a lot like mixture component 4 in the second model, so they were commuted?
Right. So this is the limitation of the matched pair lower upper bound approximation for the KL divergence. If that's the case, or in fact you want it to be more general and look at taking the distances between Gaussian mixture models where you've got different number of components in the two, then you end up using, for example, some of the variational approximations to the KL divergence rather than the matched pair one.
So, sorry, but when you're doing this, you take a bipartite matching in order to match the pairs? I'm asking about the case where there's the same number of components in both.
Yeah, so on this one, it's a matched pair one, because what you're typically doing is, imagine you start with a UBM,
yeah,
and then you map adapt that UBM to the training or the enrollment observations of speaker 1, sorry, the verification one of speaker 1, speaker 2, etc. And so because we've map adapted it from this general model.
We'll keep them kind of aligned. Okay,
but you can use any, you can actually set this up for any of the approximations to KL divergence that you want to.
sure.
So in fact, you can actually work it out. You just take the closest one if you want to. So this really, if we go back to what we were looking at when we looked at the standard, very nice static style kernels, where you could do a nice low dimensional operation and effectively work out dot products in high dimensional spaces. This is kind of not quite so true for this, because what we're having to do here is we're actually having to do dot products in quite a high dimensional space. If you think that you're dealing with, say, 1,000 components in your GMM, each of those components is built on 39 dimensional data, you've got a 39,000 dimensional feature space that you're taking dot products in. It's not, you can do it, there's not a problem there, but it's not quite as nice as when we were dealing with all the static kernels that we had before. So let's move on to another form, which are generative kernels. They kind of have this overall form which says we're going to take the kernel operation between two observation sequences. Again, will depend on a set of parameters, lambda. And what we're going to do is we're going to extract, in some way, a score space, some function of the observations given the model parameters lambda. And we'll have it also dependent on some metric. And this gives us, again, a nice sort of kernel operation where the score space defines really the nonlinear mapping from our observation sequence into a fixed dimensional feature vector. So if we take a score space in a parametric form, this says, well, let's just make the score space some estimate of the model parameters lambda, which maximize the log likelihood of our data from each of our speakers. Well, this really just says, give me a score space which just looks at the parameters of the distribution associated with speaker I and speaker J. So really, it's exactly the same as our GMM mean-Supervector kernel when we have the appropriate metric, the appropriate G associated with it. But it's more general than that, because it's kind of got lots of fun things you can do with it now. People that work in speech recognition like to adapt models to particular speakers or noise conditions or anything else. So these have also been used where you actually take what's called a maximum likelihood linear regression transformation. You work out an MLR transform for speaker I, an MLR transform for speaker J. We simply use those as the score spaces. We can take the dot products and we've just got an MLR transform kernel. We can also do this for cluster adaptive training, etc. So that's all quite nice, but we've kind of got another option for this. Once I've got my generative model, what I could do is, rather than defining a score as the parameters associated with that generative model, I could define it as the space which is defined by the derivative of the log likelihood of the observation sequence with respect to my model parameters. Has exactly the same size of feature space as if I just picked the model parameters, but I've now defined it in a very, very different way. It's now defined in terms of derivative evaluated at my current model parameters. So if you actually took this where you took a single model for all speakers, effectively you take your universal background model, we take the derivatives with respect to that, it really is exactly the same as the Fisher kernel, which is used in various biological sequence work. The Fisher kernel actually was really motivated, really trying to extract structure from unsupervised data. But when we do verification, we've got supervised data. So we can do other things. We can sit there and actually say, well, let's define a score space, which is the log likelihood ratio of two models, where one's, say, the target speaker that I'm claiming the identity of, and the other one's a UBM. I could then take the log likelihood ratio. Well, that's nice, because that's actually the score space that we normally use for GMM-based classification. But I then append onto it derivatives with respect to the log likelihood of the observation sequence with respect to the parameters from the UBM, the parameters from the speaker-specific model. So this is really quite nice. We've still got a fixed dimensional score space from two sets of generative models. What's even nicer is that you don't have to stop at just taking the first derivative. You can keep going. You could take the second derivative along with all the cross terms, third derivative, fourth derivative. And each of these give you different bits of information depending on the nature of the generative model that you're using. So you've got these two forms. They're actually quite closely related. You've got derivative models, which are the derivatives of log likelihood of the observation given parameters. You've got parametric models, which are simply, you've got a generative model, you work out the maximum likelihood estimate of parameters for them. So we'd be surprised if they weren't related to one another. And we can actually get that very clearly from the fact that if you imagine estimating your model parameters in some gradient descent or ascent-based scheme, you'd say that the update of your model parameters is your current model parameters plus some learning rate times, well, the derivative of the log likelihood evaluated at your current model parameters. The left-hand side, in many ways, is your parametric kernel. The right-hand side, excluding the lambda n and the eta, is your derivative kernel. So we can actually map the two forms to be the same by saying if we make the learning rate independent of the observation sequence, then the metric that we use, well, we can adjust that appropriately to account for the eta. And if we also use a stationary kernel so that the kernel operates simply as some function of the difference between the two features. So if we look back and looked at the radial basis function kernel, that was a stationary kernel. The lambdas will appear in both, and so will disappear when we're looking at the difference between the two. So it's not surprising. Both can be used for speaker verification, and they both work. What's nice about this is that when we set them up so these conditions aren't true, we can actually combine the two sets of kernels together and actually get gains by looking at getting sort of this extended score space based on both parametric and derivative generative kernels. I would actually say that the derivative kernels are actually better than parametric kernels, because parametric kernels, you're only ever stuck being able to get the parameters. Whereas when you look at derivative kernels, you can take as many orders of derivative and keep going as you want to. So you've actually got this additional flexibility for it, which come from looking at derivative kernels. For those of you who sort of know lots of other kernels, you can actually relate many of the features associated with the score space of derivative kernels with lots of other forms of kernel that you see in the literature. So if you have marginalized camp kernels and you look at the standard forms that they take, well, they actually turn out to be almost identical to the scores that come out taking the derivatives with respect to component priors of a GMM. They just happen to have very, very similar forms other than a constant offset. The last thing to talk about is really the form of the metric. When we looked at taking generative kernels, we took a score space, inverse of the metric, score space transpose, inverse of the metric, score space. So what is the metric that we should use? Well, kind of the default one and the simplest one to use would make it maximally non-committal. That is, we're going to weight all dimensions exactly the same. Well, that actually turns out to just say, well, let's just take the metric is given by the expected value of the score minus the mean transpose. Exactly the same way as the Mahalanobis distance metric. It's kind of nice. If we used a Fisher kernel with ML trained models, this G turns out to simply be the Fisher information matrix. When you look in the verification literature and the speaker classification literature, you find that you can actually play with this metric to give you some nice attributes. So you can actually do nuisance attribute projection by taking this metric and using the metric to get rid of dimensions that aren't useful for verification or are, for example, heavily sensitive to changes in the session. So this is quite nice. You can also do the same with in-class covariance normalization. So, yep.
What does that expectation mean there?
It's the expectation over all the observation sequences.
Like in some set of... Oh,
so if you had an infinite amount of training data, had the perfect distribution associated with it, it's the expectation over that.
So you can't just derive it from the model?
Well, you can actually use the data. You normally just take an empirical approximation to it. You take all your training data and work out.
Would you have enough training examples? Because it would be very high dimensional.
Yeah, so a lot of times to simplify your life, which is what we normally try and do, we take a diagonal approximation to it a lot of the times. You don't have to. There's various ways of projecting
Do you
down.
use this in practice? Or this is just an example?
Yeah, this is what I use in practice.
So in the diagonal approximation, you're essentially looking at the empirical variance of each of your components in the score space and then using the inverse of that.
Yeah, so it's a really, really basic, simple form.
And that's why you said that if there are some components which are highly sensitive to some extraneous factor, they'll have large variance so that G will then kill its contribution.
So a lot of these, well, when you look at these forms, they're normally based more on the full space, and they use other approximations to handle the case when they get very, very large. You do other simplifying approximations, and sometimes just project down using PCA, for example. So these sequence kernels are really very, very common. You look at any state-of-the-art verification system, there's normally some attribute sitting in there which is a score coming from a support vector machine using a form of sequence kernel and combined with various other schemes to give you your final verification outcome. So they're very common in speaker verification, speaker classification, but not so much in speech recognition. So it's kind of interesting to think, how could I take the same concepts that we use for sequence kernels in verification and look at doing them for speech recognition? So
I had a detailed question, but if you could just back up a little bit
Yep.
to your metric. So I was thinking specifically about maybe speaker verification, and I'm thinking, like, there are many speakers in your training, and if you're going to do a yes/no verification for each, I can imagine G being dependent on the speaker versus G being just a global.
the UBM,
Okay.
yeah.
So is there a reason? So I guess what I'm trying to ask is, how tailored to the particular speaker, a pair of speakers should G be, or do you really believe that G is a global metric that you just apply across it?
It's not that sensitive.
Okay.
I think we have actually done experiments where you can work out G for each speaker, or you can actually work out G as an average for all speakers.
All right.
So
Go on, yeah.
what I'd like to do is take the same concepts and see how we could apply them to speech recognition. But it's kind of subtle difference. So far I've really been talking about text-independent speaker verification, where we kind of don't really care that much about interframe dependencies. Sort of concentrated and said, well, let's just use Gaussian mixture models, which kind of just ignore the interframe dependencies. So for ASR, we care a lot more about this. So how can we actually deal with this? So if you look at the generic dependency modeling that goes on, we sort of say if I want the likelihood associated with an observation sequence, well, what we'd really like to do is to say we get a form where, let's just break this up into a product of conditional distributions, and we just keep going, and this has got a strict equality. But at the end here, we've got the probability of observation at time t given all the previous observations and the model. This is, of course, completely impractical. So what we do is we say, well, we're going to have to introduce some conditional independence assumptions. And we can do that in two ways. We could say it's conditional independence given the observed variables, or we can introduce latent variables. But even given the dependence, it actually gets quite interesting when you look at this, sort of how all of the dependencies interact with each other. But I'm not really going to go through the bottom bit. So everyone knows that what we really do for speech recognition is we actually introduce a latent variable model. And the latent variable model on the left here is a sort of the form that you read in speech recognition papers. The form on the right is a dynamic Bayesian network, which various people are now doing a lot more in this, giving in the speech world as well. Where this really just says the left-hand form gives us the state and the state topology and transitions we can use. The right-hand form gives us the conditional independence assumptions associated with a hidden Markov model. And they really are that the observations are conditionally independent given the state that generated them, and the states are conditionally independent of each other given the previous state. Very, very nice. Allows us to now break up that horrible sequence of where we're working out the probability of the observation sequence. We had all the conditional independence ones. It's now broken up into a nice form. Given the state sequence, we can simply product the observations given the state sequence. That's great. Allows us to work out the likelihood associated with an observation sequence, but it really is a very, very poor model of speech. It's basically piecewise constant. So we don't really like it from that perspective. So what can we do? Well, one way is to say, well, let's add additional dependencies onto this. Let's make an observation at time t plus 1 a function of the preceding observations at time t and t minus 1. And let's extract features based on those, as well as features based on my current observation. So if we then look at this within the complete concept of members or mixtures of members of the exponential family, which is what we always use. So this is a member of the exponential family. Likelihood of observation sequence, some normalization terms, some reference distribution, then exponential of the natural parameters times the sufficient statistics extracted from the observation sequence. Normally, when we deal with Gaussian mixture models, we say given the state, we extract the observation and the outer product of the observation squared. So when we've got this sort of setup, what we have is we have sufficient statistics. We say, well, let's, for example, extract out the observation at time t times the observation at times t plus 1 and observation at time t plus 2. So this is a sort of sufficient statistics that we would extract from the observation sequence if we had a dynamic Bayesian network of this form. The problem is that if you imagine you've got 1,000 observations, what exact set of dependencies do you want to extract from it? How far back should you go? Do you actually, this is 39-dimensional feature vectors, exactly what set of features do you want to extract from it? It becomes absolutely vast what you could do, and basically it's impractical. So what we'd really like to do is, can we come up with some systematic way that says, given an observation sequence, can I come up with a set of sufficient statistics from that observation sequence that I can just get in a nice systematic fashion? Well, we've kind of already answered that problem, because the sufficient statistics that we extract from the observation sequence need to be of a fixed dimension, because we're going to have to take the dot product of that with the natural parameters, which are also going to be of a fixed dimension. So exactly the same problem as when we deal with score spaces associated with sequence kernels. So what we can do is we can simply say, let's say the sufficient statistics associated with an observation sequence are the features of the score space from whatever sequence kernel I choose to use. The question then is, what does this mean in terms of the dependencies that you've got? So if I take my generative model and use an HMM as my generative model, and then take derivative with respect to the parameters of my HMM, does this help me in any way in terms of dependencies? Do I get anything that I don't get from my standard HMM? Well, if we look at one of the elements of that score space, we take the derivative with respect to the means, or the log likelihood, and we find that simply the sum over all times, the posterior of being in a particular state, J, particular component M, times the inverse of the covariance matrix of that state component pair times the observation minus the mean. Very nice standard form. But what's interesting about this posterior in here is actually a function of my complete observation sequence. So though my HMM said I'm conditionally independent given the state that generated me, when I work out the derivative of the log likelihood of an HMM with respect to the model parameters, it turns out to be a function of the complete observation sequence. And it gets even more interesting when you take higher order derivatives. You end up with joint probabilities of being in at a particular time instance t and t plus 1 of particular sequences of state and components, given the complete observation sequences. So we've actually introduced longer term dependencies on the whole observation sequence, which basically gives us very different conditional independence assumptions from the underlying generative model that we use to extract that score space. So that's kind of fun. And we can keep adding whatever forms of derivative, higher order derivatives, derivatives with respect to different model parameters. We can keep doing that as much as we want, and adding in a systematic fashion elements to the sufficient statistics that we extract from an observation sequence. So that all sort of sounds fun. So as an example of what goes on with it, as everyone loves made up simple examples that illustrate that what they do is bound to work in real life, well, let's take something where we've just got a very simple two symbols, A and B, and we say for class 1 we have the symbols AAAA, BBBB, so they're all the same. For class 2 we have AABB or BBAA. So if I train a couple of HMMs on this data, two-state HMMs, and irrespective of whether it's class 1 or class 2, if I train it in maximum likelihood fashion, what we find is that we basically get the same model. The probability of A is 0.5, probability of B is 0.5 for state 2, A is 0.5, B is 0.5 for state 3, and we get no information. It's the same model for class 1 as it is for class 2. So what this means is that when I try and classify with these, I get no information. And that's actually given by the first row on the table on the right, where we see that log likelihood of the data from class 1 is exactly the same as the log likelihood of the data from class 2. So let's now take the derivative. This is a discrete HMM, so we take the derivative with respect to the probability of generating the symbol A from class 2, from state 2, which is given by this line. Now suddenly we've broken it from being all the same to being 0.5 minus 0.5, 0.3 to minus 0.3. So we've gained information because we've appended things onto the score space. We've got information there. What's even nicer, if we now take a second derivative with respect to it. Yep, Dan?
I'm a little bit confused. You say you trained the HMM separately on the two different classes that happen to have the same answer?
Yeah, because of the weird symmetry that we've got on this. There's no reason why it should do anything else.
Surely the derivative should all be 0 with respect to the model parameters.
No, because I've actually trained the data on both. It needs to train it on both the sequence 4As and the sequence 4Bs.
Oh, so this is just. Oh,
so for a particular observation sequence, though it is the total values will of course be 0. For any particular observation sequence, it won't be 0. So once we take the second derivative within a state, we've now got this minus 3.83, 0.17, minus 3.28. I think even more fun is we take the second derivative between states. So one is the derivative with respect to state 2 generating A, and the derivative with respect to state 3 generating A. what we come up with is the bottom line here, and the bottom line is linearly separable. So it's great. We've turned out a task where you actually have the same HMM for both class 1 and class 2, and by taking derivatives with respect to it, we can actually classify data. So this kind of, hopefully, would be a nice motivation for doing it. So now we've got scores. How can we use them? Well, we could pick a parametric form for it. And here we've got a discriminative model parametric form. So this says the posterior of a particular class given the observation sequence and the parameters. Well, lambda are the parameters of the generative model that we've got, which we're going to use to extract the scores. Alpha are the equivalent of the natural parameters of our member of the exponential family. Still got a normalization term in there. And this is basically a conditional augmented model. Now, it's simple to apply this to isolated or whole segment models. I say the word whole segment models. It's quite simple because we can work out the scores for the whole of that observation sequence and just run with it. It's a little bit more awkward to apply this to continuous tasks. But you can do it. You sort of make conditional independence assumptions. Again, in this case, between particular classes. And then you extract scores given the segments of those classes. You simply product them up as you did before. So this is, I think, it's a very interesting form of model. It's, the results at the moment are okay, but it does need more work to really get it to work. As I said, the previous example was designed to work.
Let me see if I just understand. In going to derivatives, you lost the conditional independence.
Yep.
And then in applying that model, in order to make it feasible, you have to introduce new
Conditional independence, yeah.
Okay.
But this is a conditional independence assumption.
Oh, yes, so there's different information being generated. Yeah, I understand.
So what you'd like, so this is where it comes back. Well, so to get around that, you could use a non-parametric form. So non-parametric forms would allow you to take the whole observation sequences for all sorts of things and then look at those. So that's the alternative. So this is sort of, so now the application I'm going to look where I give some numbers is SVMs for noise robustness. So in many ways, it's kind of quite interesting. So an SVM really is a non-parametric form of classifier. So what we're doing is we're combining a parametric classifier of the HMM with a non-parametric technique support vector machine, as well as equivalently combining a generative model with a discriminative function. This gives us some nice attributes. We have our parametric form will allow us to do speaker or noise compensation approaches, which we know all about in speech recognition. So that should hopefully remove some of the outlier issues that are commonly associated with non-parametric techniques. At the same time, we've got a non-parametric model, so that we should be able to have dependencies over whole observation sequences, but because we're using the score spaces from our generative models, the actual nature of those dependencies will depend on the generative models and the scores that we choose to extract from those generative models. So what I'm going to look at in terms of these...
Let me see if I understood you. So what you're saying is that if I wanted to distinguish between phone classes, I might want to look at the derivatives of the acoustic likelihood relative to the means of the phone classes.
Yeah.
But since there's going to be speaker and other noise kind of variability, if my model had some of these MLR transforms sticking around and doing all those, then I would use all those in fitting the data and computing the likelihood. But I'd compute the derivative only with respect to the phone class means and ignore the global transform.
Yes, that's basically, so we'll do that. That's actually kind of the next slide, or the slide after.
The idea.
That's the idea.
What you meant by saying the generative techniques help you take care of other nuisance things.
Yes, because what you're going to do is rather than having, you're not going to see in your training data, if you take the example of noise, you're not going to see observations of all word sequences in all noise conditions.
Right.
So what you'd like to be able to do is say, well, let's keep the power of having of a non-parametric technique and using the whole sequences, but can we normalize it in some nice way to account for noise? So the form that I'm actually going to look at is going to be using derivative generative kernels, maximally non-committal metrics. So one thing that we do on this is to say that because we know that the log likelihood ratio is actually the most discriminative term that we've got there. We know that's basically how we normally classify things with HMMs. We look at the log likelihoods coming out. I expect that term to be slightly more discriminative than taking the derivative of component 12 of state 7 of an HMM. So we'd like to weight it a little bit more. So because I've chosen to use a max mean non-committal metric, what I do is I simply add on some epsilon times the log likelihood ratio, this SVM, where this S here is the score coming from the SVM. So let's say this is Sanjeev's thing. So what we're doing now is let's actually look at the issues of adapting SVMs to speaker and noise conditions. Well, this is the form of the decision boundary that comes out from an SVM. It's simply a sum over Lagrange multipliers times the class label times the inverse of the metrics times the score space associated with each of your training examples. So I've got a choice when I want to adapt this. What I could do is I could adapt my Lagrange multipliers and try and adapt the Lagrange multipliers of all of my training data to a particular noise condition. You can do some approaches sort of related to that, but it's painful. So let's not do it. Let's simply take this generative score space and look at adapting the kernel, the score space, to the particular noise condition associated with the observation that I'm using either in training or test. So what happens, the overall framework we're kind of aiming at here is we're going to leave the Lagrange multipliers the same. So we'll end up with a noise or speaker independent SVM classifier, but we're going to keep swapping the kernel so that that kernel, that generative kernel, is noise or speaker dependent. So all we need to do now is to have some method for adapting the parameters of our generative model to speakers or noise conditions. That's what we do all the time. So we adapt models using CAT, constrained MLR, linear transformation approaches. Or what I'm going to look at in terms of this work, where I'm looking at noise robustness for it, I'm going to look at using vector-Taylor series compensation, which all you really need to know about is just a model-based approach that allows you very, very rapidly to try and compensate an acoustic model to a particular noise condition. And so what we're going to do is we're just going to fix Lagrange multipliers of our training data and keep swapping around the score spaces. The task that I'm actually going to look at is continuous digit recognition. So of course, if I had a sequence of 6 digits, 6 digits gives us a total of about 1 million possible sequence classes. That's painful. So what we're going to do is we will actually take our HMM, we're going to do an initial recognition run, we're going to force align it, and then what we'll do is, given the alignment for a particular word, we're going to reclassify just given those word level alignments. So we can just extract scores given word boundaries and just classify those. It's related to acoustic code breaking. I'm doing a very, very simple way of mapping my SVM classification to the multi-class problem. I'm just doing 1v1 majority voting. We can do other things. We tried tree-based classifiers as well. They all work about the same.
The 25 is this Venkataramani.
Yeah. The ASRU 2003 paper. So what's the overall score that we do? Well, this is the process. We take noise-corrupted speech in at the top. We then do model-based compensation to adjust our generative model to it. We then use that in 2 ways. We go down, we do HMM-based speech recognition. That gives us the word boundaries for what's going on. We also then feed it in. We take those model compensated generative models. We generate generative kernels and score spaces from them. We also then take a noise-independent SVM. We combine it all together to do SVM-based recognition. Derivative.
Mark?
Yeah?
SVM-based stuff. You were talking just now about doing like per word or per digit. But your whole generative thing isn't that for the whole sequence of digits?
No, once I've got the word boundaries, I've actually taken...
generative stuff for each
You just do the generative stuff given the word boundaries.
Okay.
So it just, it really was making my life simple. So what's nice about this is the derivative generative kernels are really quite nicely suited for this, because what happens with those is that, as Dan was implying earlier, is that when you have these derivative kernels, when you sort of got a match, you expect the scores to be, on average, 0. So provided I'm mapping my generative models to each of the noise conditions, for any word in a noise condition that matches my generative model, I'll drive its score towards 0. So that's nice. So these should all kind of be consistent with each other. So looked at this on a couple of tasks. Anyone who's done lots of fun experiments with noise-robust speech recognition will be very familiar with Aurora 2. It's basically TI digits with noise artificially added on. The configuration doesn't really make that much difference. I'm doing ML-based estimates of the VTS model parameters, etc., etc. Basically, it's just continuous digits, whole word models, 3 components per state, quite a simple one. The other one is a little bit more interesting. It was supplied to us by Toshiba Research. We had a large phone-based recognizer. They actually had real data trained in a car. Rather than having a simple 3 components per state, it was more like, I've got a mental blank, 12 components per state in our acoustic models. And we took this at a range of noise conditions. So if we look at what's going on, so what we've got is on the right, we've got the change. If you remember, I took epsilon times the log likelihood ratio of the HMMs for it. If we actually look at that, so 0 says just take the SVM score. And if we look up here, we can see that the score from just doing vector Taylor series compensation, I've not given the uncompensated model parameter scores for this. They are 70s, something like that. Enormously bad. It's just not worthwhile putting them up.
And that's because you're trained on the
I trained only on clean, yeah. So we've got 9.8, 9.1, 9.5 for A, B, and C. If we look at where they sit on this sort of curve, it's kind of all up here. So if we don't even take any of the scores from our SVM, we're doing pretty well. Of course, because we've taken this maximally non-committal metric, we do expect a little bit of a gain as we tune the epsilon. Indeed we do. We get a minimum around 2. It's kind of quite consistent. And it's quite nice. When we look at the scores associated with that, we can see that we're getting quite nice gains. Sort of anything from 15 to 20% relative reduction in word error rate from the VGS scheme. The VGS numbers are quite reasonable on this. For those familiar with this task, they're not bad numbers, particularly just for the simple Aurora backend, not the complicated one. And this is the HTK front end and not the ETSI front end. So again, the other numbers are all a little bit better if you wanted them. So, yep.
What's the best you could do, given that you've got a fixed segmentation coming from the HMM? Did you do an Oracle letter?
I actually didn't. I should have done. There's a simple answer to that. It's not bad, actually. I was surprised how well it worked. Oh.
I'm not familiar with Aurora ABC or just because
That's, okay, so Aurora A is what, if you do multi-style training, Aurora A is where you've got those noise conditions in your training set.
Okay.
Aurora B is just additive noise where you don't have those noise conditions in your training set.
Okay.
And this is for multi-style, which I'm not using. And C is where you've got both additive and convolutional noise,
Okay.
and you've not seen the noise conditions in your training set for multi-style training.
It's supposed to be harder as you go.
Yeah. So that was doing it on the Aurora task. If we actually look at this slightly more realistic Toshiba task, bigger models, bigger score spaces, etc., we can see that we actually, for the higher, so this you can, because we're doing model-based compensation techniques, they're actually sensitive to the hypothesis you're using, so you can actually run round, repeat the hypothesis, and get improved estimates of your VGS compensation parameters. So I've done it on 2 configurations, one where I just did the first iteration, one the second iteration. For both of them, particularly for the lower SNR highway condition, we're actually getting quite nice gains again. We're kind of dropping the error rate by 15, 20% again. From, again, this is quite a sensible VGS configuration for compensation when you've got clean training data. We don't do so well, not surprisingly, with the engine on condition, because in many ways you're just compensating for noise, and the noise, you've got very little noise, that's kind of up at 35 dB. So, sort of conclusions. We've looked, so sequence kernels are an interesting extension to standard static kernels. They allow you to handle dynamic data, which we see in a range of applications. They've really been applied an awful lot in speaker verification tasks. Don't see them so much in speech. The score spaces associated with my particular interest, generative kernels and the derivative forms of generative kernels, are actually really interesting. Viewing them from a sufficient statistics extracted from observation sequence perspective, you get interesting attributes. You get different conditional independence assumptions from the generative model that you use to extract them. And we've got this ability to adapt effectively our score spaces to speakers and noise. We can apply them to speech recognition. We've got choices. We can take parametric approaches, or we can look at non-parametric approaches. I guess what's overall interesting about looking at these sorts of approaches for speech recognition is, though we don't like HMMs, they work well. And this is kind of an approach that allows us to carry on working with HMMs. We don't throw them away. We can take advantage of any sort of developments in the HMM world, while at the same time allowing us to use, hopefully, more powerful parametric and non-parametric classifiers built on top of these score spaces, built from the HMMs rather than using the HMMs explicitly. Right, are there any questions? Yeah, bro?
Does the story change if you do discriminative training on the HMMs?
I would just expect it to all work perfectly. Wouldn't you?
Well, I mean, the derivative kernel becomes somewhat more problematic because you no longer have the guarantee of the things that...
But they should all move to similar spaces. I think that's kind of the hope.
Okay.
So it's interesting. So one thing we're doing at the moment is we're currently doing discriminative training on top of various noise conditions, VTS adaptive training style things. And yeah, we're looking to trying to bundle everything together to see what we can really get from this. My hope is that you've still got the additional information as you append things onto the score space. And you could also say, well, if in doubt, we cheat anyway, because you just increase epsilon. In fact, that's a nice clue when the code goes wrong, is epsilon becomes big, and you think, I'm just doing an HMM here. So 2 is quite a nice score for the, because it shows that we really are making a lot of use of the SVM. It might shift a little bit higher when we're using the discriminatively trained HMMs, but my belief is we're still getting additional information from it.
I have a question, but let's see for the others. Yes, Jim.
Mark, can you give us some feel for the additional complexity in terms of parameter counts of these systems compared to, let's say, the baseline generative HMM system?
So if you think that the simplest way is when we've got these decision boundaries, if you think the dimensionality of the score space is really the number of parameters in your HMM. So you kind of double it. So for each of your SVM classifiers, you kind of have to have exactly the same number of parameters. You've got a feature space which is, if I've got 50 parameters in one HMM, 50 parameters in the second HMM, the score space associated with my SVM would be 100. In practice, I skipped over the fact that in reality, we just project these down. We don't use all the features. We just do Fisher selection based on Fisher ratios to project it down. So if I get worried about the dimensionality and cost of doing the classification, I can just project down further. These were run at 1500, I think, dimensionality of the feature space.